All right, we're going to turn up the difficulty a little bit. We're going to add in an angled string. So we're going to look at this example there at the top of the page. It wants us to find the tension in the three wires. I'm going to number them T1, T2, and T3. So I'm going to want to set this up. So I notice I have multiple masses. That means I'm going to get a set of equations for each mass when I do my free body diagrams, and there's going to be a common force. T1 is going to be our common force. So the easiest one to start with is to start with this 32 kilogram one. So down there I have mg, which is going to be 32 times 9.8, and T1. So when I sum up those forces in the y direction, it's going to be 0 because it's not accelerating there. And so I have T1 minus 32 times 9.8 equals 0. And so I'm left with T1 is equal to, what did we get there? 313.6. So that is a lot like the ones we just got done doing on the page before in the packet. So what we're going to do now is, now that I know T1, now I can generate two equations to find T2 and T3. And so I'm going to get an x direction equation and a y direction equation. That's going to get me my two equations. But what do I do with these tensions that are at angles? All right, so let's start drawing our free body diagram. So I have T1 pulling it down. I also have gravity, mg. Now, this one was 32 kilograms, so they were telling me the mass. This one is 175 newtons, so they're telling me the weight. So I know that m times g is 175 newtons. T2 acts this way. And remember, whenever we talk about tensions, it's along the string, away from our object. So this one is pulling away in this direction. Now, I personally like to have my angles next to my free body diagram. So I see this 53 degrees over here. So I'm going to go ahead and I'm going to make this 53 degrees. All right. The reason I'm going to need that angle is, just like with angled launch last chapter, we do have to resolve this into components. So we'll have to figure out, okay, how much of that T3 is pulling up and how much of that T3 is pulling to the side. And so I have T3 cosine of 53 here because it's adjacent to the angle. And I have T3 sine of 53 there because it's opposite. Now, as you can see by my picture, my free body diagram here, it gets full fast. So good rule, draw these big so that you can fit all of that stuff on there. Another good habit is, once you get this done, and whenever you resolve these, you can kind of put a little squiggly on it to show that, hey, I resolved it, and that vector is no longer there, it's only the components. I like to go ahead and redraw my vector with just the ones that are left over. So I have T1 pointing down. I have that 175 newtons pointing down. I have T3 sine 53 pointing this way. I have T2 pointing that way. And I have that T3 cosine of 53 pointing up. The reason I like to redraw this is, really helps me identify which forces are in my y direction, which forces are in my x direction. All right, so let's go ahead and generate those equations. We're going to start with the y direction. So the sum of the force in the y direction equals 0. It's not accelerating. It's a first law problem. So I'm going to add these up. So I have T3 cosine 53 minus T1 minus 175 equals 0. And then in the x direction, the sum of the force in the x direction, also 0. I have T3 sine of 53 minus T2 equals 0. So my plan here is to use T1, plug it in, solve for T3, get a number. Use T3 over here, plug it in, and solve for T2. So let's go ahead and do that. So T3 cosine 53 equals 175 plus T1. Divide the cosine 53 over, so I have T3 is equal to 175. Substitute in my T1s plus 313.6, all divided by the cosine of 53. When you type that in your calculator, make sure you have parentheses around that stuff on the top, or do that first. What we end up with here when we plug in for finding T3, you should get 812 newtons. So T3 is 812 exactly? Okay, roughly, I guess, 812 newtons. Now that I know T3, I can find T2. So T2 is going to equal T3 sine of 53. So we just move that T2 over, plug it in, and so I get T2 is equal to that 812 number times the sine of 53. Again, make sure you're using those exact values when you substitute in. And so I get T2 is equal to 648.4. And newtons would be that. So these problems can get large. So I end up with drawing my free body diagram, step one, generating equations for each object. All right. Each object can have up to 2. So this one doesn't have an x direction equation because there are no forces in the x direction. So I would just get 0 equals 0. Not that exciting. This one, however, does have x and y, so I will get 2 equations for that one. And so you can tell this one is a little bit more involved. All right, so what we're going to do next is a practice problem for you. So let's go on to the next video.